absolute extrema. That's what we're going to talk about today. Actually, this is the last topic about extrema. In fact, this is the last topic about the derivative at all. We've talked about the derivative for quite some time. After this, we're going to talk about something completely different. A nice little change of pace. For now, though, the last thing is absolute extrema. This is kind of like relative extrema, but it turns out actually absolute extrema, finding the absolute extrema is even easier than the stuff that we've been doing lately. So this will be a nice little romp, if you will. Here's a little conundrum I have for you that's related to the topic of absolute extrema. This is a true fact I learned a few years ago when I went hiking with my kids to the highest mountain peak in the state of Connecticut, our great state of Connecticut. We went to the top of the highest mountain peak in the state of Connecticut, which is not all that tall. After that, I learned on the internet that the highest mountain peak in Connecticut is not the highest point in the state of Connecticut. What do you think of that? Here's the conundrum. Think about that. How is that even possible? And let me just say, there's no trick to this. I'm not talking about like some tall tower or some big long rope or no nonsense like that. All right, the explanation is completely ordinary and has no funny business. Okay, it is a fact. The tallest mountain peak in Connecticut is not the tallest point in Connecticut. How can this be? While you think about that, let's talk about absolute extrema. The idea behind absolute extrema as opposed to relative extrema, here's a function. I wanted to do this. How about that? Can you find the relative extrema? This is something that we've talked about at length. The relative extrema are these sort of mountain peak points and also the valley bottom points. All right. There are relative maxima and relative minima. These are the maxima, right? These are relative maxima. That means these points, their y values are greater than all the nearby y values. And there are relative minima. That would be these ones down here. These ones, their y values are lesser than the nearby y values. What absolute extrema is about is not considering nearby anything. It's just about what's the biggest value overall and what's the smallest value overall. And if you think in the real world about when people want to find these extrema, oftentimes what they're really looking for is absolute extrema. Like, for instance, if you're looking at, if you're running a business and you want to maximize your profits, you want to find the highest possible profits, not like a profit level which is higher than all the nearby profit levels, whatever that means. You just want the highest possible profits, right? Or the lowest possible expenses or whatever. All kinds of examples where you care about the biggest or the smallest or the most or the least. Oftentimes, what you really are looking for is absolute. The biggest value overall, not just of the nearby ones. And typically there's only one of those. Like in this picture here, the absolute maximum is right here. This is the absolute maximum. It's just the y value which is bigger than everything. This one is a relative maximum. It's bigger than the nearby ones, but it's not overall the biggest. This one is the biggest. And where's the absolute minimum on this picture? Actually, this picture doesn't have an absolute minimum if we assume that these curves continue to go down on the ends, which is what I typically mean. These y values will just go down forever. There is no absolute smallest y value because the y values continue to drop forever. So it is sometimes there is no absolute maximum or minimum. Sometimes there is no absolute maximum or minimum, but there will be provided we focus on a closed interval of the domain. Check it out. So this function here, this one actually has no absolute minimum or maximum because the values today go up forever over here and they go down forever over here. So there is no absolute minimum or maximum, but there will be if we are only focused on a closed interval domain. For example, so here I'm going to say no absolute max or minimum. But what if we only consider the values on this interval from 2 to 6? Okay, that would be here. This is 2 to 6, which is here. So only considering these ones, I only look at this part of the picture, right? Oh, I got squeaks. Only looking at that part of the picture, then there will be an absolute maximum and an absolute minimum. So on this interval from 2 to 6, the absolute minimum would be here, is at x equals 4, right? That's the absolute minimum. And where's the absolute maximum? Where the y value is the highest? It's on the end right there, all right? So the absolute maximum is x equal 6, all right? So the moral of the story is, even though functions overall, they may not have a highest point because they might just keep on going up forever. If you only look at a portion of the graph, then they can't go up forever on your little portion. And so they must have some maximum value, which will either be at one of these sort of peaks and valley points, or it might just be on the end. Let me write down this basic observation as a theorem. This sort of basic idea has a name. This is called the extreme value theorem. Extreme meaning maximum or minimum. The extreme value theorem. It says if f is continuous and we only consider a closed interval of the domain, then f of x has an absolute minimum and an absolute maximum. An absolute max and min. All right, so what we're going to talk about today is how can you find the absolute maximum and minimum. Let's just look at a specific example. How about this? F of x equal x squared on the interval -1 to 2. So in absolute extrema problem, you will always be given a function together with a closed interval, and your job is to find the maximum and the minimum. Now, we can do this just by looking at the graph. Everybody knows what f of x equal x squared looks like on a graph. It looks like a parabola, and these points are -1. So this goes up to 1, right? Because -1 squared, the y value would be 1. And then it goes over to 2 here, which would go up to 4 there, right? And I'm only looking at this part of the graph. Only looking at that part of the graph. What is the absolute maximum and the absolute minimum? The absolute minimum is there. So here the absolute minimum is at x equals 0, and the absolute maximum is abs. I wrote abs with 2 B's. Please like and subscribe. At x equal 2, right? That's where the absolute maximum is. All right. Really what we want to do, as usual, this is easy to do if you're looking at the picture. You can just pick out where's the highest value and where's the lowest value. Really, we would like to be able to do this even if we don't see the picture. If I just give you a formula for something in an interval, can you tell me where the absolute maximum and the absolute minimum are? Where might they occur? Well, they might occur, the maximum might occur like at one of the sort of mountain peaks in this function, or the minimum might occur at one of these points, which the sort of valley points, or just for like coincidental or random reasons, they might be on the ends, right? Like this one, this end is not a maximum or a minimum because it happens to be in the middle. This end, though, ends up being the maximum overall on this interval. So this fact is super important. I'm going to write that. This is the principal fact which allows you to find the absolute extrema without looking at the graph. When f is continuous on a closed interval, the absolute extrema always occur at the critical numbers, that is like the mountain peaks or the valley points, at the critical numbers or at the interval endpoints. This, by the way, is why it's important that the interval be closed. It must be a closed interval in order for all of this to work, because you need to guarantee that the interval endpoints actually count as real x values. If the endpoints are excluded, like if the interval is not a closed interval, that means one of the endpoints is excluded. And in that case, you'll lose one of the absolute extrema, perhaps. So this is what allows us to find the absolute extrema. Our strategy is simply find the critical numbers, which we know how to do. We've done this over and over again. And find the endpoints. That's very easy because you're always just told what the interval is. And then you just check each y value. And pick the maximum and the minimum, right? The absolute extrema can only occur at the critical numbers and the endpoints. There's not so many of those, right? I mean, you find the critical numbers, typical examples we do, there's like maybe two or three, I don't know. And then you got two endpoints. All you got to do is just check all of the y values and see which one is the biggest and see which one is the smallest. And that must be the absolute minimum and maximum. Let's just do a couple. All right, find the absolute extrema for this function, f of x equals 3x squared minus 12x plus 1, on the interval minus 1 to 3. Let's do it. What I said, find the critical numbers and find the endpoints, and then you just check all the y values for all of those points. So let's find the critical numbers. As we always do, we're going to take the derivative, set the derivative equal to 0, and also say when the derivative does not exist. So f prime of x is here, 6x minus 12. I'm going to set this equal to 0. F prime equals 0 would say 6x minus 12 equals 0. Solve for x. So equals 12. X equals 2. All right, and then we also need to think about f prime does not exist. We're looking for 0 in the denominator or something in this formula, but there is no such place. There's no way that this could fail to exist. So I'm just going to say never. F prime does not exist. Never. F prime always exists, so we don't have to consider that. We have only one critical number. Now I'm going to make a chart. This is not like the chart for increasing, decreasing business. It's quite a bit simpler. All we got to do is check the y values. And we're checking the y values for every critical number, which was 1. We just found it was 2. There was only one critical number. And also, we need to check the interval endpoints, which in this case are minus 1 and 3. All right, so this one is here because that's a critical number. And then these are here because they are the endpoints. Every example you ever do will include all the critical numbers and the two endpoints. All right? How do you find the x and the y values? We know the x values. How do you find the y values? You just plug those numbers into the original function. You can use your calculator for this step. It's not so hard to do this by hand in this example. I plug x into the original function. Make sure you're not plugging into the derivative here because you want the y value. So I go 3 times 2 squared minus 12 times 2 plus 1. What's that? This is 3 times 4. Minus 24 plus 1, that's 12. Minus 24 is negative 12. Plus 1 is minus 11. Okay? All right, how about the endpoints? I plug minus 1 into here. I go 3 times minus 1 squared minus 12 times minus 1 plus 1. That's 3 plus 12 plus 1, 16. And finally, I plug 3. All right, 3 times 3 squared minus 12 times 3 plus 1. This is 3 times 9, 27, minus 36 plus 1. That's negative 9 plus 1, negative 8. All right? These are the y values. Now, the absolute maximum has to be one of these. It's just whichever one is the biggest. It's 16. And whichever one is the smallest is the absolute minimum. So this is the absolute maximum. And this is the absolute minimum. That's all there is to it. Let me just write my answer. I think I can squeeze it in down here. The absolute maximum is at x equals 2, where, if you care, y is, that's the minimum. So the absolute maximum is at x equal minus 1. In that case, the y value is 16. And the absolute minimum is at x equals this one, 2. And the y value is minus 11. That's that. Let's try one more. There's not really much that can go wrong with these guys. There's one slight thing you need to be careful of. I will say, beware values that are outside the interval. You'll see what I mean in a moment. Let's try f of x equals, Let's try this function f of x equals 3x to the 4 plus 8x cubed minus 18x squared on the interval minus 1 to 1. All right? Same old business. Find the critical numbers, make a chart with the critical numbers plus the interval endpoints. So, critical numbers, first of all, take the derivative. F prime of x is 12x cubed plus 24x squared minus 36x, right? Simplify, I can factor 12x out of that. And what's left is x squared plus 2x minus 3. And then this I can factor also, x minus 1x plus 3. All right, this is the derivative, f prime of x. To solve f prime of x equals 0, you just equate each of these to 0. I get x equals 0. Well, it's 12x equals 0, which means x equals 0. X minus 1 equals 0, which means x equals 1. X plus 3 equals 0, which means x equals minus 3. And these are my three critical numbers. You should also think about when the derivative fails to exist, but the derivative always exists here because there's no denominators or any other funny business. Let's make it a chart. All right, my three critical numbers were, what were they? I forgot. 0, 1, and 3. And then I also have the two interval endpoints, minus 1 and 1. I guess I don't need to write the one twice, right? Sometimes by chance, one of the interval endpoints will also be one of the critical numbers. You don't have to check it twice. Here's what I meant when I said this at the very beginning. Beware values outside the interval. For this function, we are only considering the x values between minus 1 and 1. In this example, that means I should not consider this 3. This, I crossed it out because it's outside the interval. Outside the interval, right? If you forget about this, then you can get sort of a false positive. You can think that maybe this is actually the absolute maximum or minimum, even though that point is not even inside the interval that we're talking about. So make sure you exclude points that are outside the interval. It'll save you some work because you won't have to find the y value for that one. Also, it might prevent you from screwing it up. Okay, find the y values. I just got to plug these three. I have to plug 0, 1, and negative 1. Lucky for me, those are easy numbers to plug into this formula. So when I plug in 0, well, would you say I get 0 every time, right? 3 times 0 to the 4 plus 8 times 0 cubed minus 18 times 0 squared. This is 0. Okay, when I plug 1 in, I get 3 times 1 to the 4 plus 8 times 1 cubed minus 18 times 1 squared. Any power of 1 is 1, so this is 3 plus 8 minus 18. That's 11 minus 18 is negative 7. And then finally, negative 1. It's the same, only some of these will have a flipped sign, right? This is 3 times minus 1 to the 4 plus 8 times minus 1 cubed minus 18 times minus 1 squared. Minus 1 to the 4 is 1, so that's 3. And then this is going to be minus 8 and then minus 18. 3 minus 8 is negative 5. Then minus 18 will be minus 23. All right, these are my values. I choose the biggest and the smallest. 0 will be the maximum, but you didn't expect that. Between these three numbers, right, your choices are 0, negative 7, or negative 23. 0 is the biggest, and negative 23 is the smallest. In conclusion, the absolute maximum is at x equals 0, y equals 0, and the absolute minimum is at x equals negative 1, where y equals negative 23. There you are. Can we resolve the conundrum that I presented at the beginning? Perhaps this discussion of absolute extrema has made you have an idea of how this could be true. How could it be true the highest mountain peak in Connecticut is not the highest point in Connecticut? The highest, you want to think of it in terms of absolute extrema. The highest point in Connecticut is the absolute maximum of the elevations, right? And as we know, the elevation does vary continuously, so we can use the extreme value theorem, and it says the absolute maximum, the absolute highest elevation, must occur at a critical number, which is like a mountain peak, or on the end of the interval. It turns out, this is a true story about the state of Connecticut. The state of Connecticut, this is like near the border with New York. So this is Connecticut and New York, and I'm just drawing some sort of cross-section of the state of Connecticut. It looks like this. There's a bunch of mountain peaks. Oh, that squeaks. A bunch of mountain peaks, right? Here's the highest peak in Connecticut. But then near the border, the elevation continues to go up, and there's like another peak in the state of New York over here, all right? But the highest point in the state of Connecticut is here. This is the highest point. And it is not at a mountain peak. All right? It's because the absolute maximum can occur at a mountain peak, or it can occur on the end point. Now, the state of Connecticut is not like the number line. It's more like a 2 or 3-dimensional thing. But the same is true. Actually, there's a whole theory of calculus in higher dimensions called multivariable calculus, which you might, we have multivariable calculus classes if you want to take them. And they talk about there is a sort of 2 or 3-dimensional version of the extreme values theorem, which basically says the same thing. The absolute maximum value occurs at a critical point or on the edge of the domain, on the boundary of the domain. And in the case of, in the real world, the state of Connecticut, the highest elevation occurs on the boundary of the state. It's a true fact. Tell your friends. Amaze your moms.